Good evening, ma'am. Am I audible, ma'am?
Good evening, sir. Yes, sir, you are audible, sir.
Okay, ma'am. Thank you so much.
Sir, you can start, sir. Let them
Okay.
join.
Okay, ma'am. Okay. Good evening, students.
Good evening, sir.
Yes, I hope you all might have attended the test given by me on moving charges and magnetism, and also magnetism and matter. Have you completed the test?
Yes, sir.
Okay. So actually now I have planned to discuss the solutions for the numerical problems. So each and every numerical problem, we are going to discuss the solution. Okay. So let me share my screen first. Are you able to see my screen?
Yes, sir.
Okay. So I think this is the first question which I gave you. Okay, a straight conductor carrying a current I splits into two parts as shown in the figure. The radius of the circular loop is capital R. The total magnetic field at the center P at the loop is, okay. So this is your diagram, and you can see a straight conductor actually, okay. It is actually a straight conductor carrying current I, and it splits into two parts as shown in the figure. The radius of the loop has been given, and the current after entering this position, that is this point, okay. So the current after entering this point, it splits into two, that is I1 on this portion and I2 on this portion, and we need to calculate the magnetic field at the center P due to the entire loop, okay. So that's what we have to do, and now we shall discuss the solution for that. So usually whenever you have a loop, current carrying loop, okay, current carrying arc subtending some angle theta, then the magnetic field due to the loop is given by this formula, okay. As you can see from the screen, this is the formula which you need to use to find out the magnetic field due to a current carrying arc, okay. When it subtends an angle theta, then you have to use this formula to calculate the magnetic field. So using this formula, actually we have the larger arc AB, okay. Larger arc AB means, so you can see from this diagram, this is the larger arc. So this arc from here to here, okay. This is the larger arc. So this arc subtends an angle 270 degree here, okay. So this larger arc subtends 270 degree here. So based on that, we have to use the formula for magnetic field here. B1 equal to mu naught I1 by 2R into 270 by 2 pi. So here instead of theta, I am just using 270. So as you can see from the direction of the current flowing through the arc, then this magnetic field should act in the inward direction. That is according to the right hand thumb rule. Okay. So then the magnetic field due to the smaller arc. So smaller arc, as you can see from this diagram, the smaller arc is subtending an angle 90°. So we have to substitute 90 instead of theta here. That is B2 equal to mu naught I2 by 2R into 90 by 2 pi. Okay. So current values are differing. So you have to keep that in mind. Here I have used I1 and here I have used I2. Okay. You should keep that in mind. And here the current flow is in opposite direction to that of the first arc. So based on thumb rule, this magnetic field should act in outward direction. Now the resultant magnetic field is given by, for V1 I am actually using the negative sign. Okay, as I have told you earlier, the magnetic fields are acting in opposite directions. Based on the thumb rule, you can identify the direction of flow of the magnetic field. So this is V1 and I am taking V1 as negative mu naught I by 4 pi r into 270 plus mu naught I2 by 4 pi r into 90°. So here these two arcs can be considered as two resistances in parallel combination. Okay, two resistances in parallel combination. That means V1 equal to V2, that is I1 R1 equal to I2 R2. So these two arcs, as you can see from the diagram, this arc carrying current I1 and this arc carrying current I2 can be considered to be a combination of two parallel resistors. So in the parallel combination, the potential difference is same. So V1 equal to V2, that means I1 R1 equal to I2 R2. So that means the wire is an uniform one. So R1 equal to R1 by R2 equal to L1 by L2. Okay, how did we arrive at this equation? So here, you know very well the resistance R is equal to rho into L by A. Okay, here they are telling us that the wire is uniform. That means the area of cross section is same for both parts of the wire. So area of cross section is same. So they are made up of the same material. So rho is same. Only L is differing. So that means R is proportional to L. So for two portions, it is R1 by R2 equal to L1 by L2. Okay. So this length of the arc, how can we find out the length of the arc? This is the equation. Length of the arc is equal to radius into angle. So based on that, here I am substituting R as the radius. Okay, here you see R is the radius and the angle is 270°. And for the smaller arc, R is the radius and the angle is 90°. So here R1 by R2 equal to L1 by L2. So here you know very well, you see I1 R1 equal to I2 R2. We have mentioned here. That means I1 by I2 equal to R1 by R2 by R1. Actually, I1 by I2 equal to R2 by R1. So based on this, we can actually write 90 by 270°. I1 by I2 equal to R2 by R1. R2 by R1 means you can see this expression. Okay. So this is R1 by R2. So what I am doing is I have to put R2 by R1. That will give you 90 by 270. That will be 1 by 3. So I1 by I2 equal to 1 by 3. So we know very well I1 R1 equal to I2 R2. So for that you will be getting 3I1 equal to I2. So here you see I1 by I2 equal to 1 by 3. Okay. I1 by I2 equal to 1 by 3. So that means 3I1 equal to I2. So after that, what you have to do is you have to put here Br equal to mu naught by 4 pi r within the bracket minus 270 I1 plus 90 I2. How did we get this? Because we have that resultant magnetic field here. Okay. So this I1 and I2 we know very well. I1 3 I1 equal to I2. So here instead of I2 I have to put 3 I1. So here I have done that 90 I2. So instead of I2 I am putting 3 I1. Then I have to simplify this 90 into 3 270 I1. So this is minus 270 I1. 270 I1 minus 270 I1 will give you 0. So the net magnetic field is 0, and that is option A. And I hope you all can understand the solution for this problem. If you have any doubt at any point, you can ask me. Okay, you please don't hesitate. If you have any doubt at any point, okay, of the discussion which is happening today, if you have any doubt, you can unmute yourself and you can ask your doubt. Okay, then only you can learn how to solve this problem. Then the second question, it is here a cylindrical conductor of radius capital R is carrying a constant current. The plot of the magnitude of the magnetic field B with distance d from the center of the conductor is correctly represented by the figure. So what they are telling is they are asking us to find out the dependence of the magnetic field B with distance d from the center of the conductor. So according to the question, they are having a cylinder here. Okay, they are having a cylinder here, and for that cylinder, from the center of the cylinder, the distance is taken as small letter d. And what is the relation of the magnetic field with the distance? That means how this magnetic field B depends on the distance d from the center of the wire. That is represented by 4 options. We have 4 graphs here. We need to find out which is the correct graph representing the relation of the magnetic field B with distance d. Okay. So here you see this is the cylinder. Okay, cylinder can be considered to be made from many concentric circles. Okay, many concentric circles. So here you see the radius of the cylinder is capital R, and from the distance, and the distance is d from the center. Okay. So at some distance d greater than R. Okay. That means here at this point, what is the magnetic field? How can we calculate the magnetic field? So by Ampere circuit law, integral B dot dl equal to mu naught I, and the magnetic field can be taken outside. Integral dl equal to mu naught into I. So when you integrate this dl, what you have to do is you have to find the total circumference of the circle having the radius d. Okay, so b into 2 pi d equal to mu naught I. That means b equal to mu naught I by 2 pi d. So here you see what is the relation. Here the magnetic field B is inversely proportional to the distance d. Okay, where at a point outside the cylinder. Okay, at a point outside the cylinder. That means your B is very much greater than capital R. Okay, for that you can see the magnetic field is inversely proportional to B. And now on the surface we have to see. On the surface, what is the equation? So we have found out the magnetic field at some point here. Now on the surface of this cylinder, okay, on the surface of the cylinder, somewhere here, okay, what is the magnetic field? So that we have to find out. So B equal to mu naught I by 2 pi R. Okay, B equal to mu naught I by 2 pi R. Instead of B, I have to substitute R. And the magnetic field at a point inside, okay, magnetic field at the point inside, the current varies usually. Why the current varies? because the current per unit cross sectional area of the cylinder you need to multiply by the cross section of the loop. So current per unit cross sectional area is I by pi r square. So that you multiply with the cross section of the loop by d square. Okay. Then what you will get? You will be getting I prime equal to id squared by r square. From this equation, you can see you can cancel out pi and id squared by r square. So here the current is id squared by r square. What is the magnetic field? Mu naught I prime by 2 pi d, and instead of I prime you have to put id squared by 2 pi r squared into d. Okay. So this is mu naught id by 2 pi r square, and all the other terms will be cancelled. So here you see the magnetic field is inversely proportional to r square. Okay, or directly proportional to d. You can call that way. It is directly proportional to d. So this is the first region at a point inside the cylinder. The correct option is actually here B, because in B you can find this kind of graph. Okay. At a point inside the cylinder, the magnetic field is proportional to D. So that's why the linear variation of the graph is here. Okay, B is directly proportional to D. So D increases, B also increases. So the graph follows this path, and at D equal to capital R, it reaches the maximum. After that, you can see from this expression, B is inversely proportional to D. Okay, here. From this expression, you can see B is inversely proportional to D. So outside the cylinder, it is like this. Okay, B is inversely proportional to D. So it is falling down. So the correct graph is option 2. Okay. Now we shall move on to the third question. An electron moving in a circular orbit of radius r makes n rotations per second. The magnetic field produced at the center has the magnitude. So electron moving in circular orbit means it constitutes some current, because electron is a charged particle. So when it is moving in circular orbit, a charged particle in motion, it constitutes a current, and due to the current you will be getting magnetic field. Okay. So what is the value of the magnetic field produced at the center when your electron moves in a circular path? So that we have to do. And first of all, we need to calculate current I equal to Q by T. Here Q is the charge of the electron, so Q equal to E. And since it is a circular motion, the time T is given by the time period of revolution of the electron. So time period of revolution is represented as capital T. So I equal to, instead of Q, I have to put E, and instead of T, I have to put capital T. And this time period is equal to 2 pi by omega for the circular motion. So this omega can be taken to the numerator, omega E by 2 pi. So this omega is nothing but 2 pi into frequency, that is 2 pi into N, and E by 2 pi you will be having. So this 2 pi and 2 pi will get cancelled. Now the current I equal to NE. Okay, current I equal to NE. So now the magnetic field at the center is given by, due to the circular coil, it is mu naught I by 2R. We have learnt earlier, magnetic field due to the circular coil at the center is mu naught I by 2R. So here, instead of I have to put NE. Instead of radius, I have to put smaller. That is mu naught NE by 2R. And this is the right answer. That is option D. Okay, option D. Okay. So now, the next question is, in the product F equal to Q into V cross B, that is equal to Q into V cross. So instead of this B, I have to write this equation. B I cap plus B J cap plus B naught K cap. Okay. So what does it mean actually? So B is a vector quantity. Okay. Magnetic field B is a vector quantity. That means the magnetic field can be represented as, since it is a vector quantity, vector B equal to bx I cap plus by j cap plus bz k cap. Okay, this is the expression. For this case, you are having, for the present case, you are having, instead of bx, it is b. Okay, instead of by, it is b. Instead of bz, it is b naught. Okay, so in that way you have to take. So they have given q equal to 1, b equal to 2i plus 4j plus 6k, and f equal to 4i minus 20j plus 12k. Now they are asking what will be the complete expression for b. Okay, complete expression for b means you have to find out the value of this b and b naught, and then you have to substitute in this equation. Okay, b equal to bx I cap plus by j cap plus bz k cap. In this equation you need to substitute. So for that you need to find this cross product. Okay, v cross b, cross product you need to find out, and then multiply that with q. Q is 1, so there is no problem. And f they have given 4i minus 20j plus 12k. So you have to equate this force with whatever expression you are getting here. Find out the value of the magnetic field. So let us do that now. So here you can see B cross B means it is a vector cross product. So you have to write this in determinant form. I, J, K. So for velocity you have 2, 4, 6. So the component should be written here 2, 4, 6, and it is B. So as I have told you earlier, B means Bx, By, Bz. Okay. Now you have to simplify this determinant. That you can do it in this way. So I into 4bz, that is what you have to do. You have to hide this this row and this column. I think you know very well about the determinant. Okay, that is you have to hide this column and this row. Okay. So since you are considering I cap, you have to hide this column and this row containing I cap, and then you have to see 4 into bz minus 6 into by. Okay. So like that you need to do. So this is 4bz minus 6by, and minus j cap. Minus j cap means what you have to do. You have to hide the column containing j and hide the row containing j as well. Okay. So in that case, you will be getting 2 into bz minus 6 into bx. Okay. I hope you all can understand this. If you have any doubt, you can ask me. So plus k cap into, then what you have to do? You have to hide the column containing this k. So this k, and then the row containing k. So that means you have to hide this thing. Then what you will be getting? 2 into by minus 4 into bx. So like that you have to put, and after that you have to put f equal to q into b cross b, and then what you have to do is you have to continue. Here you can see q equal to 1 4, f equal to 4i minus 20j plus 12k. Okay. So after simplifying this, here you know very well bx equal to by equal to b and bz equal to b naught. So you know very well it has been given in the question. You have to equate the coefficients. So here f value, f equation you have to equate the coefficients of I, j and k by this. So equating the coefficients, you will be getting b equal to minus 6 and b naught equal to minus 8. Now after getting the values of b and b naught, okay, you can substitute in the expression for b. In the question they have given you, b is nothing but bi cap plus bj cap plus b naught k cap. We have found out the values of b and b naught. So the complete expression is minus 6i minus 6j minus 8k cap So this is how you need to solve the problem. The correct answer is now option B. Okay, it is minus 6i minus 6j minus 8k cap. So option B is the right answer. Do you all understand this, students? Any doubt you are having up to this point? Any doubt you have?
No, sir.
Okay, okay. In that case, let us proceed further. So this is the next question. Ionized hydrogen atoms and alpha particles with same momenta enters perpendicular to a constant magnetic field. The ratio of the radii of their paths RH is to R alpha will be. Okay, you have ionized hydrogen atoms and alpha particles with same momenta enter perpendicular to a constant magnetic field. The ratio of the radii of their paths will be. So they have given the options. We need to find out the solution. Here, since they are entering perpendicular, it will be in circular motion. Okay. Since they are in circular motion, the centripetal force is provided by the magnetic Lorentz force, BQV. Okay, BQV. So, magnetic Lorentz force is BQV, the centripetal force is MV P squared by R. And that will give you R equal to mvp by bq. Here vp is the perpendicular velocity of a particle. So we know very well the momentum is given by momentum p equal to m into vp. Okay, momentum p equal to m into vp. So what we can do is, instead of this mvp, what we can do, we can simply put p, r equal to p by pq, and given the in the question they have given that momenta of both particles are same. So magnetic field is same, momenta is also same. That means the radius of the circular path is directly proportional to 1 by q or inversely proportional to q. Okay. So the radius is inversely proportional to q. Now we can easily find out the solution. For ionized hydrogen atom, what is the charge? It is simply the charge of the proton. Because ionized hydrogen means what you are doing is you remove the electron from hydrogen. Okay. When you remove the electron from hydrogen, it will become H plus. That means it has only one proton, and the charge of the proton is E. For alpha particle, okay, for alpha particle you have 2E. Okay, for alpha particle you have 2E. So how it is 2E? I think you all know very well. Alpha particle is nothing but helium, right? So alpha particle is nothing but helium. So here they are mentioning that ionized hydrogen and alpha particles. That means alpha particle is also ionized. Ionized helium nucleus. So you know very well, for the alpha particle the charge is 2E. So we need to find out the ratio of the radius of hydrogen and alpha particle. So RH by R alpha is equal to Q alpha by QH. That will be 2E by E. Why it is coming like this? Because inversely proportional relation. The radius is inversely proportional to the charge. So it is 2E by E. That will give you 2:1. That is option D. Okay. We are having option D, 2:1. And then the next question is, an alternating electric field of frequency nu is applied across the D's radius R of a cyclotron that is being used to accelerate protons. Protons are having mass m. The operating magnetic field B used in the cyclotron and the kinetic energy K of the proton being produced by it are given by. So we have an alternating electric field of frequency nu. It is applied across the D's of a cyclotron. So it can be considered as a memory-based question. Okay, we need to find out the magnetic field value and also the kinetic energy value. We can answer this question simply based on the derivation part which we use for cyclotron. Okay, so how can we solve this problem? So here you see, this frequency nu equal to EB by 2 pi m. So that's the equation which we have discussed already in cyclotron. And the kinetic energy equal to half mv square. Radius is equal to mv by EB. Okay, everything we have discussed in the theory part of the cyclotron. And velocity equal to pi r by t by 2. Why it is pi r by t by 2? Or it is nothing but 2 pi r by t, because it is a circular path. So the circumference divided by the time period is the velocity. So 2 pi r by t. So 1 by t is nothing but the frequency. So 2 pi r into nu, that is the frequency. Now what is the radius r? It is mb by eb here. Okay, mb by eb. So instead of this v, I have to substitute this 2 pi r into nu. So that's what I have done here. 2 m into 2 pi r nu divided by eb. So now what is the magnetic field value? So that will be actually, you see here, this b can be taken to the other side. Okay, this b can be taken to the other side, and r can be taken here like this. So this r and r will get cancelled. I think you can understand this equation. So if you don't, I can write it here also. In this equation, okay, p is equal to m into 2 pi r into nu divided by e into r. So this r and r will get cancelled. It will leave you with 2 pi into m into nu, okay, divided by e. So from this equation, I am writing like this: p equal to 2 pi m nu by e. This is the value of magnetic field. How to find out the kinetic energy? Here half mv square. So instead of p, we have derived the expression. So v equal to 2 pi r into nu. So v squared means 2 pi r nu whole squared. That will give you 4 pi squared r squared nu squared. Already you have 2 in denominator. This 2 and this 2 squared will be cancelled. You will be left with 2. So that is 2m pi squared r squared nu squared. This is the value of magnetic field. And this value of magnetic field 2 pi, this is the value of kinetic energy actually. And this B value and this kinetic energy value is found in option C. So option C is here. That's the right answer. The next question is: a beam of electrons passes undeflected through mutually perpendicular electric and magnetic fields. If the electric field is switched off and the same magnetic field is maintained, the electrons move. Okay. Actually, what they are telling is you have electric and magnetic field mutually perpendicular. When you pass electrons through this, okay, it passes undeflected. That means the net effect of this electric and magnetic field is 0 on the electron. So that's why it is passing undeflected. Now what happens is, if you switch off the electric field and the magnetic field is maintained, that means now it is only under the influence of magnetic field. What is the path of the electrons? And what will be the path of the electron? They are asking you. Okay. So for that, we shall discuss here. So as I have told you, the electron is passing undeflected in the presence of both electric and magnetic field. So that means the force due to electric field Ft, force due to magnetic field Fm. When you add both these things, it will be 0. But now electric field is switched off. That means you have only the force due to magnetic field. So magnetic field alone is there. So the charge actually moves along a circle. Okay, the charge actually moves along the circle since E is perpendicular to B. So even though it is switched off, E is perpendicular to B, and the charged particle, okay, it will move along the circle. That will be option B. Okay, that will be option B. And the next question is question number 8. A metallic rod of mass per unit length 0.5 kg per meter is lying horizontally on a smooth inclined plane, which makes an angle of 30 degree with the horizontal. The rod is not allowed to slide down by flowing a current through it when a magnetic field of induction 0.25 Tesla is acting in the vertical direction. The current flowing in the rod to keep it stationary is, okay, you have a rod, metallic rod of mass per unit length lying horizontally on a smooth inclined plane. The rod is now not allowed to slide down by flowing a current through it when a magnetic field of induction 0.25 Tesla is acting on it in the vertical direction. The current flowing should be found out, and we shall see how to solve this. This is the rod, okay. It is in cylindrical shape. It is lying like this, having an angle theta. So the weight of the rod can be resolved into mg sin theta and mg cos theta component. So mg sin theta component is balanced by the force. Okay, balanced by the force. So they have told us that the rod is prevented from falling. That means it is in equilibrium condition. So equilibrium condition means this mg sin theta should be balanced by this f cos theta. So mg sin theta equal to f cos theta. So F is the magnitude of the force experienced by the rod when placed in a magnetic field, and I is current flowing through it. So how the rod is experiencing the force? Because it is a current carrying conductor, right? A current carrying conductor placed in magnetic field experiences a force. So you know very well the formula F equal to BIL sin theta usually. Okay, we have already discussed that also. So vector F is equal to IL cross B. Okay, like that we will be putting. So when the angle is 90 degree, it is BIL sin 90 degree, and that will give you BIL. So that's what we have done here. It is ILB. Okay, it is ILB. So mg sin theta will be equal to f cos theta, as we have told already. So f is ILB, so ILB cos theta. So from here I need to find out the current value. So I am bringing all the terms to the other side. So mg by lb, this is sin theta by cos theta. That will be tan theta. Okay, that will be tan theta. So this is m by l into g tan theta by b. Okay, the sin by cos will give you tan. So m by l g tan theta by b. So we have been given the value of m by l, that is mass per unit length, that is 0.5 kilogram per meter, and instead of theta, that's also given 30 degree. Capital B, magnetic field value, is also given. The current you can calculate. M by L is 0.5 and G is 9.8, and the magnetic field is B. Tan 30 degree will be 1 by root 3. After substituting all these values, we will be getting 11.32 ampere. So that you can find in option D. So option D is the right answer. Okay, option D is the right answer. Now question number 9. A square loop ABCD carrying a current I is placed in near and coplanar with a long straight conductor XY carrying a current I. Then the net force on the loop will be. So you have a square loop ABCD carrying a current I placed with a long straight conductor XY carrying a current capital I. The net force on the loop will be. Okay. So this is the diagram. First of all, you need to understand the diagram. So this is XY. Okay, this is XY carrying a current I. Okay, and you have the loop. Okay, square loop like this. You have the square loop like this, carrying a current small I. Okay, carrying a current small I. So as you can see from the diagram, the direction of this I will be like this. Okay, the direction of I will be like this. On this arm AB, it is in this direction. On this arm BC, it is in this direction. On arm CD, this is in this direction, and arm DA, the current is in this direction. So you can see arm AB, okay, current arm AB and arm CD. They both are in opposite directions. So here, as you see, we know very well that when the current carrying conductors carry current in the same direction, then what will happen? They will actually attract each other. Okay, they will attract each other. So this arm will be attracted to the wire. At the same time, this arm and this wire carry current in opposite direction. So this end will be repelled. Okay. So like that, you need to understand this. So the force of attraction can be expressed as FBA equal to mu naught I small I L by 2 pi into L by 2. Why it is L by 2? Because this arm AB is at a distance L by 2 from this wire. And then the next arm CD. Okay, the next arm CD, it carries current but in opposite direction. Okay, so that will be repelled by the wire. That force is given by mu naught IL by 2 pi into 3L by 2. Now, what is the net force on the loop ABCD? Usually, the force FPA should be greater because this arm is nearer to the wire. So, the force on this arm BA, it will be greater minus F into CD because these two forces are in opposite direction. So, what you can do is you can substitute the expression for FBA and the FCD. Okay, we have FBA and FCD. We can substitute the values here, simplify it, and then we will be getting 2 mu naught II by 3 pi. Okay, this is the force on the loop. So this is option D. Okay, this is option D. Now question number 10. You have a rectangular coil. Okay, you have a rectangular coil of length 0.12 meter and width 0.1 meter, having 50 turns of wire is suspended vertically in a uniform magnetic field of strength 0.2 Weber per meter square. The coil carries a current of 2 ampere. If the plane of the coil is inclined at an angle of 30 degree with the direction of the field, the torque required to keep the coil in stable equilibrium will be, okay, the current carrying loop kept in a magnetic field, rectangular coil, okay, current carrying loop or a rectangular coil, current carrying rectangular coil, okay. So if it is kept in the field, what is the torque required to keep the coil in stable equilibrium? So that we need to find out. Okay, so this is the diagram for it, and you have the formula. Tau equal to NIAB sin theta. Okay, NIAB sin theta. So it is 30 degree means the remaining angle. Okay, with the magnetic moment that will be 60 degree. So the theta should be 60 degree. Okay, because the angle with the magnetic field is 30 degree. That means the remaining angle is 60 degree here. So that 60 degree you need to put sin 60 degree. So NIAB sin theta. N is the number of turns. Okay, N is the number of turns. So that is 50 into current. Current is 2 ampere. Okay, NIA. A means area. Area will be length into width. So 0.12 into width 0.1. Okay, the magnetic field is 0.2. That is put here, and you have sin 60 degree as well. And after substituting these things, the torque is 0.20 Newton meter. Okay, the torque is 0.20 Newton meter. So this is the torque required to keep it in stable equilibrium. That is option B. And now, question number 11. A coil is in the shape of an equilateral triangle of side L. Is suspended between the pole pieces of a permanent magnet such that vector F is in the plane of the coil. If due to a current I in the triangle, a torque tau acts on it, the side L of the triangle is given by. Okay, first of all, you need to draw the diagram for this. You have an equilateral triangle of side L suspended between the pole pieces of a permanent magnet. So let us see the diagram. This is the equilateral triangle suspended between the pole pieces. South pole, north pole. Okay, suspended like this. And the side of the equilateral triangle is small l. Okay. So here, what they are telling is F is in the plane of the coil. So if due to the current I in the triangle, a torque tau acts on it, the side L of the triangle is. So tau equal to M cross B. Okay, tau equal to M cross B. You know very well. M is I into A, and M cross B means actually it is MB sin theta. Instead of M, it is I into A into B sin theta. Now, what is the area of this triangle? That is root 3 by 4 L square, because area of an equilateral triangle is given by root 3 by 4 into A square. A is the side. Okay. So instead of side here, we have L as the side. That is L squared, and theta equal to 90 degree. So IAB sin theta instead of A, root 3 L squared B sin 90 degree. Sin 90 degree value 1. So tau equal to root 3 by 4 I L squared B. So now we need to find the value of L. So you can bring all the terms to the other side. So that will give you L is equal to 2 into tau divided by root 3 BI, power 1 by 2. Okay. So this is how you need to solve the problem. Okay. The next question is, current is flowing in a coil of area A and number of turns N. Then magnetic moment of the coil M is equal to. So this is a straightforward question. Current flowing in a coil having number of turns N, magnetic moment of the coil. So it is a memory based question. So the correct option is NIA. Okay. M equal to NIA. This is the right option. I think you won't be having any difficulty in solving this. Then question number 13 is related to moving coil galvanometer. They have mentioned that the current sensitivity of a moving coil galvanometer is 5 divisions per milliampere, and its voltage sensitivity, that is angular deflection per unit voltage, is 20 division per voltage. The resistance of the galvanometer is, they have given the current sensitivity and also the voltage sensitivity, and asking the resistance of the galvanometer. First of all, the current sensitivity equation is Is equal to theta by I, that is nothing but NAB by K. Okay. Current sensitivity Is equal to theta by I, so that will be equal to NAB by K, where K is nothing but the restoring torque per unit twist. And voltage sensitivity is Vs equal to theta by V. Vs equal to theta by V, and the theta value here you can see. So this theta by V, okay, theta by V means, so here you see it is NAB by K, okay, NAB by K, I by V, okay, NAB by K, I by V. So why we are writing like this? Here you see, so this theta, okay, this theta is nothing but from this equation, okay, from this equation you can find theta, okay, you can find theta. So So theta is equal to N AB divided by K into I. Okay. So this is theta, and you are substituting this theta here. Okay. You are substituting this theta in this place. So theta by V. So instead of theta, NAB by K into I. And this V. Okay. So this is the NAB by K into I. This is theta, and V we have. So here this I by V. Okay, I by V is nothing but resistance. V by I. Actually, we know very well V equal to IR. Okay, V equal to IR. So that means I by V equal to 1 by R. I by V equal to 1 by R. Here also you have I by V. Okay. So here also you have I by V. That means the resistance is in denominator. So instead of I by V, you can put RG. Because V equal to IR. So that means 1 by R equal to I by V. So that instead of that I by V, you have to put resistance of galvanometer in the denominator, and from this RG equal to IS by VS. Okay, here you see this RG. Okay, this RG. So let me clear the annotation so that we can understand better. Here you see this is NAB by K into RG. Actually, we know we need to find out RG. Okay, so this equation can be modified like this: RG equal to NAB by K divided by VS. So NAB by K we have already found out that this is current sensitivity IS. So IS by VS is nothing but the resistance of the galvanometer. Okay. So that is done here. So resistance of the galvanometer equal to current sensitivity by voltage sensitivity. So current sensitivity is 5 divisions per milliampere. That means 5 into 10 power 3 divisions per ampere. I think you can understand this conversion. Okay, 5 divisions per milliampere. So 5 divisions per milliampere means per 10 power minus 3 ampere. So this is equal to 5 into 10 power 3 per ampere. So that's what we have done here. And the voltage sensitivity is 20 divisions per volt. So now we can substitute IS and VS values in the resistance of galvanometer. So RG equal to IS. IS is 5 into 10 power 3 divided by VS is 20 divisions per volt. So this will give you 1 by 4 into 10 power 3. Okay. That will be 1000 by 4. 1000 by 4 means it is 250. So that is 250 ohm. That is option A. Okay, that is option A. And the next question: in an ammeter, 0.2% of main current passes through the galvanometer. If resistance of galvanometer is G, the resistance of ammeter will be. So for that you need to draw the circuit of an ammeter. In an ammeter, 0.2% of main current passes through galvanometer. Resistance of the galvanometer is G. So here you see 0.2% of the main current means 0.002 into I passes through the galvanometer. Okay. So if the resistance of the galvanometer is G, then the resistance of the ammeter will be. So here, actually we are connecting a low resistance in parallel, that is RS, right? That is RS. The low resistance in parallel is RS. So through the low resistance, most part of the current flows, that is 0.9988. How did we arrive at this? Because here 0.2% of the main current passes through galvanometer. So that is 0.002I passes through the galvanometer. Galvanometer setup is like this. Okay, galvanometer setup is like this. So here 0.2%, this This A symbol is actually used to denote it is an ammeter. Okay, you should not get confused. So the entire setup is ammeter. Instead of this diagram, you can also draw like this, no issues. I will draw here. So here you are having this galvanometer, and here you are having the load resistance. Okay, this entire combination is ammeter, and this is the galvanometer resistance G. Through the galvanometer, you are having 0.2% of the total current, that is 0.002 I. And through the low resistance, you are having 0.9988. The remaining current flows through the low resistance in parallel. So that is represented as RS. RS means shunt. So here you see, since both of these resistances are in parallel, galvanometer and shunt resistance are in parallel, you can use this equation. Ig into G equal to I minus Ig into S. Okay, that same equation you have to use. From that, you can find out the resistance of the low resistance actually. This RS you can find out. But they have asked us to find out the equivalent resistance of ammeter. Equivalent resistance means the total resistance of ammeter. Here we have just found out the low resistance value, that is 1 by 499 into G. So here this G and this shunt are connected in parallel. So for finding the effective resistance, you need to use this formula. 1 by R equal to 1 by G plus 1 by RS. After simplifying this, you will be getting G by 500. Okay, G by 500. So that is option C. And the next question is similar to this thing. The resistance of an ammeter is 13 ohm and its scale is graduated for a current up to 100 ampere. After an additional shunt has been connected to this ammeter, it becomes possible to measure currents up to 750 ampere by this meter. The value of the shunt resistance is. So initially they have an ammeter and it can measure a maximum current of 100 ohm. Okay, the resistance of the ammeter is 13 ohm. Okay, it can measure currents up to 100 ampere. So this is the ammeter. This is the ammeter. For that ammeter, they are connecting an additional shunt. Okay. So for the ammeter, you know very well. So ammeter and shunt are connected in parallel. So IA into R equal to I minus IA into S. Okay. Similar formula. So this S is equal to IA into R divided by I minus IA. So IA means the current flowing through the ammeter. Initially it is 100 ampere. So 100 ampere into 13 ohm divided by I minus IA. I minus IA means 750 ampere minus 100 ampere. So the shunt resistance to be connected here, it is 2 ohm. Okay. I think you all can understand this because what they are telling is they have an ammeter, the resistance is 13 ohm and the scale is graduated for a current up to 100 ampere. Okay. So it can measure up to 100 ampere, and when you connect the shunt, the ability to measure current goes up to 750 ampere. Okay. So here the total current is 750 minus 100 I minus IA. So after solving this, you will be getting the shunt resistance value as 2. Okay. We have discussed the solution for 15 problems today, and we shall be continuing with our discussion of the question paper tomorrow also. We will be discussing the solutions, okay, of the remaining problems tomorrow also. Okay. Now, thanks for joining the session, students, and we shall continue the discussion tomorrow. We shall discuss the solutions for the remaining questions. Thanks for joining.
Thank you, sir.
Thank you.